anytime now. There we go. All right, so some emails got sent out. Maybe you guys got this email, maybe you didn't. But they sent out an email of the schedule of how the AP exam is going to be done this year, right? How it's going to be administered this year. So they got three recent ways of administering it, right? Administration 1 is not applicable. That's the one where they were going to hold it like normal, like the regular AP exam, like was going to be the first 2 weeks of May. But we couldn't do that because it conflicts with SBAC, so juniors wouldn't be able to take the AP and the SBAC at the same time. So what we're left with is 2 types of administrations, right? Both of which are hybrid, but the dates are different for each one, right? So one of them is going to be between May 18th to May 28th, right? And this one is probably the one that we're going to be doing. Actually, they already decided. And for the paper-based exam, this is going to only be offered for Spanish language, Spanish literature, AP Calc, AB and BC, Physics 1, and Statistics. The third one, the dates go from June 1st to June 11th, and this one was a tough one for us to do because it conflicts with our graduation dates. I think our graduation date is June 10th. So if it was this administration, that means like some kids would have to take the AP exam after they graduate, and I know that that's probably not something that most students want to do. So for AP Calc right here, right, they're going with the blue in person, which means your tests for the AP exam is going to be on May 24th. May 24th. Oh God, graduation is on June 9th, not June 10th. So administration 2 is the only option, can offer possibly to 11th graders, but I don't think that's going to happen. If the majority of the students are going to be taking it on May 24th in person, I think that's the one that they're going to go with. I don't know if they're going to allow kids to do it at home, especially for you seniors, because that's the day of your graduation. So just a heads up, the exam is going to be on May 24th. I'm upset to see that it's going to be AM or PM or not, but I'm assuming it's going to be in the AM, which means it's going to be at 8 a.m. On campus. And they will have it so you will be separated by like at least 6 feet from each other. If you guys did the PSAT for you juniors, it'll probably be set up the same way. If anyone here did the PSATs, let me know. But yeah, that's that. All right. Any questions about your AP exam? Any concerns at all? I do encourage, and I actually kind of require most students to take the AP exam when they take my AP class. When I grade your final, I grade it based off if you took the AP exam or not. So if you don't take it, you still, have the final like everyone else does, but I just won't curve it towards your grade. But if you do take it, I curve your final. Just a heads up. So that's my way of encouraging you to take the AP exam. Even if you don't feel like you're ready, just take it anyways. You've done all this time, done all this practice, you might as well take it. There's no harm, no foul. There's nothing bad happens if you get a 1. Okay, it's at least you had the attempt to do it. And who knows, maybe you will pass. There's a good chance. All right. That being said, let's continue where we left off last time, right? Where we were doing these RRAM, LRAM, and MRAM, right? And MRAM stands for the midpoint, and we kind of rushed through this right here. This is kind of an interesting idea, right? We calculate the area underneath this curve, which, by the way, why do we calculate the area underneath the curve? It helps us to find particular values, right? If we know that this is a particular rate of something, if you get that area, you can find out the total amount of something between 2 endpoints, between A and B, right? So if you have a graph of a rate of somebody running at 7 miles per hour, and you clock it in for 2 hours from 8 a.m. to 10 a.m., that area that's underneath there will tell you the total distance traveled, right? If the rate is like, let's say, distance over time, right? And if you have a rate of snowfall over time, that area underneath the curve will tell you the total amount of snowfall between a set number of time, right? So that's the idea of why we calculate the area underneath it. If we have a rate, we can find out the sum of something, right? That's the application behind it. Now, we found out that if we had something that was curvy, right, we can still draw little rectangles to calculate them, but it won't be exact, right? It will just be an estimate. And we have this rectangular approximation method where we draw rectangles in here. And then we also saw, right, as we increase the number of rectangles, the area, the approximation of that area changed as we went there. Okay. Well, today I wanted to talk a little bit more about that and go in a little bit more. So when are we going to get to the calculus part of this? Because honestly, this is all just geometry stuff. You're calculating area using rectangular equations, which is something we've done in the past, right? You know how to calculate area of rectangles. Now we're just applying it to these functions. Before I do that, though, check this out. I wanted to show you this weird little notation here. There we go. So if you notice, right? If you notice, the way we calculated this area, we calculated, if it was our RAM, we calculated the function value at the right side of the rectangle, right? So this 0.25 was 0.5 squared, wasn't it? This one right here was 1 squared. You see that? This 2.25 was this 1.5 squared. This 4 was this 2 squared right here. This 6.25 was this 2.5 squared, and this 9 was this 3 squared, right? It was always whatever the function that we were dealing with squared, right? Oh, I'm sorry, yeah, the x value squared, which was the function, right? The operation of that function. So what we can say here is when we calculated this, right, we were essentially just calculating the function value at that particular point, right, multiplied by this thing right here. It was 0.5 for every single one of these, right? It was 0.5 for every single one of these. But before that, it was just 1, wasn't it? And if you look closely, that 0.5 and that 1 has to do with how many rectangles you want. If you only wanted 3 rectangles, right, and I was doing it from 0 to 3, right, that number came out to be a 1 right here. But if I was doing it with 6 rectangles and I was doing it from 1 to 3, that number changed. It was no longer 1, it became 0.5, right? And the relationship between that, between the number of rectangles there are and how wide each of those rectangles are, is based off of this formula right here. It goes off of where are you starting your problem, right? And where are you ending it to calculate that area? So in this case, it was from 0 to 3. To calculate that distance, we just subtract that. It would be 3 minus 0. And then we would simply divide that by how many rectangles I want. So to get that 1, we would divide by 3. That's how we end up with a 1 in that case. For the second one, if we did it going from 0 to 3, but I wanted 6 rectangles, if you look at this closely right here, this is how I was getting the 0.5 right there for that width. You see that? So depending on how many rectangles you want, that's going to change what you're going to multiply. That's going to make decide what the base of your rectangle needs to be. See that? That right there. Okay. That base of that rectangle, right? This right here, this 0.5 in this particular case, has a particular name for it, right? And what that name is, we call it this guy right here. If you have your rectangles from here, 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 right here, as it changes from here to here, normally we have this as an x-axis. What we call this right here, we call that our delta x, our delta x. Your delta x is basically how much your x is changing from one value to the next. So the delta x from here to here should be the same as it is from here to here, as it is from here to here. And to get the height, right, we would end up like, if it was like this curve right here, right, we would calculate it based off the right-hand side, right? So this right here would be the height of this thing. So, well, if this was a function of x, right, to calculate these areas down here, right, for this one right here, let's do this one in blue, I would be taking the height of that rectangle, so f of x, right? Let's call this x sub 1, because they're going to be a little bit different. And we would multiply that with delta x sub 1, right? How much that difference is from here to here. And then once you get that one, then we would take it and add it to this area right here. So it would be plus f of x, and let's call this one x sub 2, right? It's the next x value over. And again, the difference here is also delta x as well. So we'd multiply that with delta x. And we'll call that delta x sub 2 just in case it's like a different value, but most of the times it's the same. Most of the times it's the same. These guys are usually the same. Okay? And you do this repeatedly, right? Oh, here's the next rectangle, right? And it's on the right-hand side, so we go with plus f of x sub 3. That's a weird-looking 3, knock me. F of x sub 3, right, times delta x again, sub 3. So when you think about this, right, this area that we're approximating underneath this curve is basically the sum of these rectangles right here. This blue, this red, this purple, and then this green right here. We're summing up these rectangles, right? And we call this Riemann's sum. Riemann sum. Traditionally, we just say it's rectangular approximation. That's what we mostly assume that R stands for RAM, is rectangular approximation. But we give credit to this guy named Riemann. He was the one who came up with this method, right? And with Riemann sum, he realized like, oh, it's just the height of the rectangle is just what the frequency value is. And if you do R, then it's the right side of it. And if you do L, right, then it would be the left side of it. So instead of x sub 1 being there, x sub 1 could be over here, and this could be the height, right? Like this, if you want to do the L side instead of R. But either way, it's the same approach. Because if you do L, it's still the height of the rectangle, still the function. It's just where are you taking that function and evaluating it, and then multiplying it with the delta x. Okay, so this would go on infinitely for however many x's you decide to do, however many rectangles you decide to do. And when you do that, however many rectangles you decide to do, your delta x would change accordingly. Okay. They denote this differently. So instead of writing this infinitely, right, to add up to get all these areas underneath here, they wrote it out as a summation notation. Have you guys ever seen this before? This like funky looking backwards E? Have you ever seen this guy? That's called a summation notation. It means just to add up all the units to it. Net. Don't know what you mean, David. Net forces. Oh, okay. Yeah. The summation of forces. You're right. Yeah, in physics. That's good. Yeah, so when you sum up all the forces, that's basically the idea here. I'm summing up all the rectangles in this case, though. So in this case, I'm summing up all the rectangles when I'm calculating it with the height of said rectangle, right? And we use the letter I usually when we deal with these summations. And you know what? Let's just go with K. Right? For all the x values in there, and then we multiply that with the widths of each of those rectangles. So x sub k, like that, the delta x. Usually the delta x's are all the same, but there's a possibility that they might be different. Now this is going to happen, of course, for when k is equal to 1 for the first rectangle you have, all the way up to n, and n being however many rectangles you want. So earlier when we did RRAM with the number 6, it would be that n right there would be 6, and then you would do and have 6 elements that would be added together if n was equal to 6. And we saw that, right? We saw the 6 elements right here. 1, 2, 3, 4, 5. 6 elements that we added up together. So this right here, this is what we say is equal to the area. This is what is equal to the area, right? And n can vary from problem to problem. If n was equal to 5, then you'd only have 5 rectangles. If n was equal to 6, then you'd have 6 rectangles, right? And so on and so forth. Now, some students were doing the homework the other day. I was like, wow, awesome job on doing that homework on the first day. And some of you haven't seen this yet, but there's a couple problems on the homework that asks you to use n equaling to 100. And I was so glad the student came to ask me for help, because I'm not actually going to ask you to write out 100 elements. That's just cruel. So what I'm going to ask you guys to do instead is take a look here. There are a couple of websites that will do it for you. And I'm also going to show you how to do it on your TI calculator today. Because when you do the AP exam, since we're going to be in person, you guys can't use Desmos, which is a shame. But you will have access to a TI calculator during the exam, and that is something you can use to do these Riemann sums, right? If they ever ask you for more than like 8. Heck, even if it's more than 6, I would still use the calculator just because I'm lazy. Wait, no, not lazy. I want to be clever about it and, you know, work smarter, not harder, right? But anyways, what I want to show you guys is here on Desmos here. Check this out. Here, I Googled Riemann sums, and this guy came up right here. I thought this was pretty cool. They have an n slider here for how many rectangles you need to have. So the example here, if you have n is equal to 4, or n is equal to 5, or n is equal to 6, it does it automatically. And it also does left hand, right hand, and midpoint. So if I wanted left hand, I would have to set C equal to 0. So I'd set it like so. And there's the left hand approximation. You see how do you guys see the corners right here? These are the left hand values of these rectangles right here. Boom, boom, and boom, right? And with this thing, you're also allowed to change the function that you type in here. So what was the function that we were working with here? What was this function? It was t squared. So we go back in here, let's change it to, oh, it's already set to x squared. So this is, hey, wow, it's already set to what we were working on. How convenient. It's almost like I planned this. I didn't. But anyways, so let's take a look here. Our RAM, right? We got our RAM with 6 rectangles to be 11.375. 11.375. So let's go ahead and set this to our RAM here. Our RAM, let's read the directions. Right-handed sum rule. C needs to equal to 1. So I just move this over to 1. Like so, there's my right-hand rule. You see it? So there's my right-hand values here. 9, 6.25, 4, 2.25, 1, and 0.25. Those are exactly the ones that we got, right? And then we're supposed to calculate the rectangle areas. So if you look closely here, the bases right here is 0.5 apart, 0 to 0.5, 0.5 to 1, 1 to 1.5, and so on and so forth, right? And look at here. They do this notation, the summation from 0 to n minus, well, it's supposed to go from 0 to 3, but their formula is a little bit different here because of the way they set up their stuff. But it's close enough. It's equal to the function value of, and they have here s of I, which is defined to be this function over here, I believe. It gets a little, no, that's the graph it. Yeah, I actually don't know too much about this coding right here, but it's the same idea. It's the function value at this particular point times the width. And the width, of course, is going to be defined as, do they show the calculations for these guys? They do not, do they? They have x equals to a, x equals to b. That's the curve. Oh, here it is, the formulas. The width is equal to b minus a over n. S is equal to a plus w. This is this is a little bit more further than we need to talk about our own stuff. So they code it so they make it look pretty without us having to, they have it to fit in there. So anyways, I'm getting sidetracked again. But yeah, so that's the idea here. So now we have this nice representation here that does the same thing that we did, right? Now, of course, I had to show you how to do it by hand before I gave you these guys, these calculators that will do it for you. And I honestly say, when you do the homework for the earlier ones where it asks for like 4 rectangles, just do it by hand. It's good practice. It helps you grasp the idea. But when you get to the problem where it asks you for 100 rectangles, use a calculator that's online. I Googled Riemann sums online, and I can just give you guys this. I'll put it into your daily agenda so you guys can just use this. Actually, you know what? I'm gonna do this now before I forget. Actually, can you guys do me a favor? I'm gonna copy this link. Can you guys open it real quick? Does it take you to this this function? Does it take you to this equation? Or this type of Desmos graph? Can someone? Yep, it does. All right, sweet. So let me put that into the agenda right now before I forget. There's another site that does it as well. I'm gonna find that later for you guys. But this one is just a cool one, and it's cool to see. So let's go ahead and do that real quick. So before we did the guided notes, let's see here. Enter. There we go. And this is going to be right here. Desmos Riemann sums. Boom. That says it works. I'm going to go ahead and put that in there and save. So let's go back and, like I was saying here, check this out. You can increase the slider for your n, and you get more rectangles. So if I wanted n is equal to 10 rectangles, I could just slide it over to 10, and you can see the 10 rectangles right here. You see that? Boom, 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 boom. Oh God, I zoomed in, so I messed up the click. All right, anyways, let me zoom in a little bit more here. So check this out, check this out. You zoom in. If I wanted 10 rectangles, what do you notice? What's the width value now if I wanted 10 rectangles? What do you guys see? What is the width for it when I set the number of rectangles to 10? And Monica's saying it's 0.3. The delta x now, the width of these rectangles have gotten smaller, haven't they? They've gotten smaller. But with them being smaller, what do you guys notice about the area, the approximation of the area now compared to when it was equal to 6? What do you guys see? What do you guys observe? What do you guys notice about the area? So when n was equal to 6, here's my area, right? I have all these extra pieces right here. This right here is an overestimate. This right here is an overestimate. This right here is an overestimate. All of these are overestimates. But as I make it smaller, more small, it gets more accurate. That's right. Good. Ava, good. Monica, right. The more rectangles we have, the more accurate it becomes, doesn't it? Because the amount that we have as extras there gets cut off a little bit less and less, right? So if I zoom in here, it's a little bit, it's still an over approximation, but it doesn't quite cut off as, I'm sorry, over approximation as much. Whoa, what is this, the limit? You're getting ahead of me, David. That's where we start talking about the calculus part of this. So before we get into that, let's go ahead and get into our notes for today, right? 5.2 notes. I'm going to go ahead and copy this link and ask you guys to open this up. These are guided notes, so I will be grading these along the way. So could you please fill them out along the way? And then homework will be at the end of this guy. So go ahead and open that up. Hopefully this works. You will have to do it on Cami because it is a drawing one. But if you want to print it out, you can, and just do it on paper. You can, and then just do it. Turn it in afterwards. Like take pictures and submit it at the end of it, like you've done in the past. You can do it that way too. I just realized, yeah. So write it on your own paper if you don't want to do it on Cami, and then you could just print it out and then add it onto it yourself afterwards. Okay. So let me go ahead and do that right here. Let's get onto here and open up the notes that I did not upload onto here. Oh, knock me. How are you unprepared? It's okay. It's as easy as clicking and dragging, right? There we go. We got it up. So I'm going to give you guys a second to open this up. These are the notes here. And if you look here, this is what we were just talking about, right? Area can be approximated using Riemann sums, right? Rectangular sums. Who was this man, Riemann? Who's man? Riemann? I don't know who that is. All right. We've talked about this the other day. We have L, R, and M, right? Using the left hand, the right hand, or the midpoint of the x coordinate for each of the intervals to find the height of those rectangles. Okay? So let's take a look at this problem right here. This problem right here. Let f of x be equal to 9 minus x squared on the interval 0 to 3. On the interval from 0 to 3. Okay? If the intervals are the same width, wow, there's typos on this. If the intervals are the same width, and can you guys fix that typo? Or if you guys are in AP English, do you guys still get extra credit for grammatically incorrect sentences? I don't know if the AP English teacher still does that, but that's not the right word. If all the intervals are the same width and there are 6 rectangles, what is the value of delta x? So I'm asking, what's the width of the rectangles? What's the width of each of these 6 rectangles? So how do we calculate that, right? Remember those widths right here, that delta x? I'm going to put this off on the side right here. Delta x, right, is going to be equal to b minus a over n. So if it's going from 0 to 3, right, it's going from 0 to 3, how wide should each of these rectangles be? Well, it's going to be equal to 3 minus 0 over 6, which is going to be equal to 3 over 6, which is just equal to 0.5 or 1/2. Okay? So the widths of each of these rectangles need to be 0.5. Needs to be 0.5. So right now, I'm going to show you guys how to do this on your TI calculator. Okay? I'm going to show you how to do this on your TI calculator. You ready? If you don't have a TI calculator, you can do this on Google Sheets or on spreadsheets, but I wanted to show you on your TI calculator because, like I said, since the AP exam is going to be in person, you will be, I don't know if you'll be provided, but you will be allowed to use the TI calculator during the exam. You just won't be able to use it on your computer. We do have physical ones. I don't know if they're going to let you, they should let you guys check it out on the day of the exam and then turn it back in on the day of the exam. So if you don't have your own TI calculator, they should have one on campus for you guys to check out. But if not, I mean, if that's the, it's kind of late now. But I mean, if you guys are going to college, most of you guys should already have your own TI calculator. If not, you should look into buying one. And usually you just go onto Craigslist and buy a used one. They're kind of pricey. They're like $100 brand new. So you usually could find them for like 60 bucks used, and they still work just fine most of the time. Anyways, so let's take a look here, right? So let's do this for the L RAM on the left side, right? Left side, left-handed rectangles is right here. So the left, so here, this right here is a graph of it going from 0, 0.5, 1, 1.5, 2, 2.5, and 3, right? Can you guys see that okay? Now, the left-hand rule, right, is going to ask me to do this right here. It's going to go on the left side only. So the left side, so here are my rectangles. 1, 2, 3, 4, 5, 6 rectangles. But I want to get it from the left-hand side. So I'm going to go ahead and go over here. And this is going to be my rectangle right there. And for this one right here, right, the left-hand value is going to be using 0 right there. And then this left-hand right here will be this rectangle like so. And then I'll use the 1 like so, 1.5 like so, 2, and 2.5. Notice I don't use 3. The 6 values I'm going to use is on the left-hand side is going to be 0, 0.5, 1, 1.5, 2, and 2.5. Those are my x values. Those are the x coordinates of each of these rectangles. I'm not using the right side. I'm using the left side because that's what L6 is asking me to do. So those are the values I'm going to put into list 1. So first things first, how do you get to list? Okay, so on your TI calculator, if you guys have one, can you guys turn it on right now? And if not, just follow along with this video until you get one. And then practice this, okay? So check this out. I'm going to show you how to do this on your calculator. So we go ahead to get to list. We hit the button that says stats right here. You might look above and say, knock me. It says list in blue right there. And you're right. That's where we get to edit those lists. But we're going to go ahead and hit stat, right? And after you hit stat, we're going to go ahead and click on edit because we're going to edit these lists right here. So you have L1, L2, L3, L4, L5, L6. If you guys have taken statistics before or you're taking it right now, this is nothing new to you. If you haven't taken it before, this is new to you, and I promise you it's not that bad, okay? So normally we have, if you have an older calculator or you're using someone else's calculator, there's sometimes numbers already in there. Like, oh, there's like 53, 6, 9, and you don't want those numbers in there. You could go to each one of these elements and press delete, but it's going to take forever if you have like 50 numbers in there, right? So what you can do instead of just going to each number and pressing delete, you can go up to the very top, don't press delete. If you go to the very top and you press delete, you delete the whole list. I want to clear the list. So at the very top there, you can press clear. You'll clear the list out, press enter, and it'll have the whole list out cleared. If you go to the top and you press delete, I kid you not, this happens more often than not, you will literally delete L1. You ready for this? If I hit delete, L1 is now gone. So when I start looking around there, there's L2, L3, L4, L5, L6. I don't have an L1 anymore because I've deleted it. So if you do this, by the way, how do you bring it back? To bring back a list that you've deleted, you see above delete, there's the word that says INS. INS stands for insert. So I'm going to go over to L2 right here. I'm going to hit second. I'm going to hit INS to insert a list. You see right now that list is empty because it doesn't have a name. You get to name the list. You can name it whatever you want, but for conventional sake, I'm going to put L1 back, and L1 is in blue right over here over the number 1. So I hit second and 1. Name L1, press enter, L1 is back onto there. Okay? All right, we're almost there, guys. We're almost there. Here we go. List 1 is going to be the x coordinate for each rectangle. So right now, each rectangle is 0, 0.5, 1, 1.52, 2.5. So let's go ahead and write those values in there. 1, oh, nope, I already messed up. 0, 0.5, 1, 1.5, 2, 2.5, And that's it. I don't include 3 because 3 is not part of that left-handed rule for that rectangle that I'm drawing here, right? I only want 6 rectangles, right? And even if I wanted 7 rectangles, I still wouldn't include 3 because 3 right there would be the right side rule. All right, so we have these here. The y value is going to be equal to the y coordinate of the rectangle. And we're going to do this by using the formula in the title bar. So check this out. I could go to each one of these and then evaluate and calculate, right? What is 9 minus x squared going to be at this particular point? So it will be 9 minus 0, and I could plug in the number 9. And then over here, 0.5, right here would be 9 minus 0.5 squared, which would be 9 minus 0.25, which is 8.7. And you see this is just like knocking. This is me doing it by hand, right? And you promised me it would be an easier way. And I promise you it is. So check this out. When I come over to L2, I don't actually type in my answer for this one, right? Instead, I'm going to go up to L2 at the very top. And you see it says L2 is equal to, and I'm going to type in this equation. You ready for this? I'm going to type in 9 minus, now check this out. This is the part that's going to blow your mind. I want to do minus every number that I've placed into L1. I want all the x values calculated. So I'm going to do here 9 minus, I press second, I hit 1 again, and this is what's going to happen. It's going to do it's going to do 9 minus L1, but don't forget that L1 needs to get all those values for your x that you have needs to be squared. So check this out. I can type it in as L1, and I simply hit the squared button right there. And what is going to happen in L2 is it's going to do these calculations for all those x values that I have there. It's going to do 0. It's going to do God, not me. It's going to do 9 minus 0 squared, 9 minus 0.5 squared, 9 minus 1 squared. All I have to do is press enter. And if you look closely, everything in L2 is all your y values evaluated for those x values that are there with the equation that we've just typed out. It's kind of neat, honestly. I promise you it's kind of neat. At least I think it's kind of neat. But you see right here, we get 9 right there because 9 minus 0 squared is 9, right? How about here? We get 8 right here because 9 minus 1 squared, that's still 8. Check out this one. 9 minus 2 squared. 2 squared is 4. We get 5. Those are all the y values that we have there. Okay, those are all the y values that we have there. Okay, we're almost done. I promise you, we're almost done. Next thing up is the width of each of these. And you'll notice the width from 0 to 0.5 is simply just 0.5. The width from 0.5 to 1 is simply just 0.5 again. And it's 0.5 for all of these, isn't it? Boom, boom, and boom. There you go. The widths will change if we do different widths, but for right now, it's nice to see them nice and uniform, right? But it doesn't necessarily always have to be the same. But Riemann liked it where they're all, I don't know if I actually can't make that claim, but I know that most of our problems that we do these for, Riemann sums, usually they're the same. The only times they're going to be different is if you use a table where you don't have the specific function. And we'll worry about that when we get there. So in L3, I'm just listing the width of the interval, which is this guy right here, right? They're all the same in this particular case. It won't always be the same, but in this case it is. All right, we're almost done. We're almost done. L4 is going to be the area of each of these rectangles, right? So it's going to be 9 times 0.5, 8.75 times 0.5, 8 times 0.5. And again, if I sit there and actually physically type these out, 9 times 0.5, then there's no different from me just doing it by hand. Give me 1 second. Dog wants to go outside. All right, dog. I'm sorry. I'm ruining your nap. Go ahead. This dog is so needy. Okay, so again, if I just sit there and I just multiply each one, right? That's all that's going to happen there. And I'm like, I might as well just do it by hand. But again, the reason why we do it on this calculator, check this out. You ready for this? Let me delete that. Okay, you ready for this? In L4, if you go to the very top, if all I'm doing is multiplying every number in L2 with every number in L3, I can tell my calculator to do that for me. Simply tell it, hey, go to the very top, though. Don't do it in this box. You'll get an error because you're trying to fit all these numbers into one box. Go up to the very top there. You want to fill out this whole list, right? And in L4, I want it to equal to every number in L2 to multiply it with every number in L3. Multiply it with every number in L3. And when you do that, bam, it calculates the multiplication for you. It multiplies everything in L2 with everything in L3. Those values right there are the areas of each of these rectangles. That 4.5 is this area right here. 4.5 right there. That 4.375 is this area right here. 4.375 and so on and so forth. Those are all the areas that we have for those 6 rectangles using the left-hand rule. You're almost done. The next thing you're supposed to do is add all these up. And again, you don't have to sit there and type 4.5 plus 4.375 plus 4 plus 3.375 plus 2.5. That's too much work. Once you have those numbers in L4, all we got to do is add up all those numbers in L4. So check this out. If you hit second and quit, you come back to Blinky. In here, they call it the home screen. I call it Blinky. Blinky's better. You see, it blinks right there. Are you watching him blink? Look, he's blinking now. Blink, blink. Anyways, all the numbers that you have are in L4, and you're just trying to add them all up to get this area. If you hit second, and then the stat button, which is where it says list right there, and you go over to math, you'll see this button that does a bunch of things. It'll find the minimum for you. It'll find the max, the mean, the median. What we want is the sum. What we want is the sum. So I'm going to go there and select the sum. And I want the sum of everything in L4. And L4 is the blue button above the 4. So I hit second, 4. And now I'll go ahead and sum up everything in L4 for me. So when I press enter, that right there is the sum of all those rectangles using the left-handed rule. And I get an area of 20.125. And that's your answer. So that's us using the calculator to do that work for us. You see that? That's us using the calculator to do that work for us. Now, some of you guys might not have a TI calculator, but you should have access to it on your Chromebook. Remember, I gave you the link so you can download the app. It is free until July, so you guys can do it for my class and get yourself familiar with it. Because like I said, when you guys do the AP exam, you're going to have to use these TI calculators. Now, if I had just done this on Desmos, 9 minus x squared, let's go ahead and do this on Desmos, right? The function I'm using, also n is not equal to 87. Let's go n is equal to 6, right? Was it 6? I think it's 6 what we were doing with. And the function here is going to be 9 minus x squared. This is easy as typing in the function. And then zooming out so we can see it. Do you see the also, watch out. This is the right-hand rule. I need to set this to the left-hand rule. Read the directions. Left-hand rule, set C equal to 0. You got it, buddy. C equal to 0. Bam, right there. There's the left-hand rule as such. So check this out. These are the values we got. Here, 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 and here. Right? There's one down here as well, but that's not part of our L, right? Our left-hand rule. So let's go ahead and double check these values that we got here. So look at L sub 2, right? Our list 2, all the Y values. 9, 8.75, 8, 6.75, 5, and 2.75. And double check the widths. See the width of each of these rectangles is 0.5 from here to here. It's 0.5 from here to here. It's 0.5 from here to here. So like I agree, Desmos is so much easier when you do these things. But again, someone has to code this. And when you're doing the AP, I mean, when you're doing normal exams, if you do online exams, they won't just give you these codes. And you probably won't be able to just Google things. What's Desmos written in? That's a good question. I don't know what the language is. What language? What code language? Come on, Google. Why aren't you just auto thinking what I want? This Desmos. Use JavaScript. They use JavaScript. Nah, David, you already had the idea. If I learn JavaScript, I might be able to go work for them. But why would I want to do that? But yeah, good job. All right, so that's the idea behind there. So anyways, for right now, I don't want you to do Desmos on this activity. I want you to do it on the TI calculator. And if you don't have the TI calculator, let me show you how to do it on Google Sheets. But we'll do that afterwards. On your notes right now, can you guys, before we do the answer for R6, right? Before we do the answer for R6, can you guys go ahead and take a minute and draw what what the rectangles should look like right here for the right-handed rectangles, So it's already broken into the intervals for 6 for you already. So it's going to go 0, 0.5, 1, 1.5, 2, 2.5, and 3, right? It already breaks it out for you right there. But can you guys go ahead and draw what the right-handed rectangle should look like if this was my base, 2, 3, 4, 5, and 6. Those are my 6 right there. Can you guys go ahead and take 30 seconds, draw yourself what should those rectangles look like if you're doing it for the right-handed rule? If you're doing it for the right-handed rule, what should these rectangles look like? You should work for them how much you promote them. Honestly, Sam, like, I'm promoting it just because, you know, they did a pretty good job. You got to admit, like, before Desmos was around, we all had to learn how to use this TI calculator, and it was it takes a little bit more effort. And Desmos, you could just click and just type it in, except for when the functions weren't there. Then you had to like learn a little bit of coding, which again, everyone should know a little bit of coding. Have you guys learned how to code yet? Have you guys taken a computer science class yet? It's the future, you know, or so I'm told. I'm going to go in here and clear out all the numbers in my list right now. So just to show you how to do that, we go to L4. Don't press delete. You press delete, you're going to be in a bad time. I press clear, press enter. That clears out all the numbers. I'm going to leave the L3 in there because it looks like all of these widths are still going to be 0.5. So I'm going to leave those widths in there. I'm going to take out L2, though. I'm going to clear out L2. And I'm going to go over here and clear out L1. L1 I'm going to clear out as well because L1 is not going to start at 0. L1 is not going to start at 0. So hopefully you guys have taken that minute to draw your right-handed rectangle, right? So this base right here, the height is going to go based off the right side, which is going to go to here, right? So this one right here is going to go based off the right side, which is going to go up to this function value right here and go like so. So hopefully you have your drawings and they look like this. If not, you can fix your drawings and make them look like this right now. Do you notice that the right hand right here, this one right here, is just a flat line right there for that rectangle? It doesn't go off the ground at all, does it? Which means, by the way, that this right-handed rule, is this going to be an overestimation or is this going to be an underestimation? What do you guys think? Is this going to be an overestimation or an underestimation? What do you guys think for this right-hand rule? Yeah, underestimation. That's right, Ava. That's right, Monica. You're missing out on these areas right here, aren't you? So this is going to be an under. So remember, I asked this question the other day. Yesterday, our right-handed rule gave us an overestimation, didn't it? This example, right-handed rule is giving us an underestimation. If there was only some way we could be able to tell if something's going to give us an overestimation or underestimation, there's maybe some kind of pattern that goes on there. Oh, well, we'll never know. So let's go in here and let's get these R right-handed rule values here. So the first value is not 0, is it? The first value is what, guys? If I'm doing the right-handed rule, the first value is going to be 0.5. You see that? Because I'm taking the right side value. That's this guy right here. You see that? These are the values I'm going to be taking. These right side values right here. So it's going to be 0.5, 1, 1.5, 2, 2.5, and 3. That's what I'm going to plug into L1. So I'm going to plug that in right there. 0.5, 1, 1.5, 2, 2.5, and 3. Those are my x coordinates for the right-hand rule. Okay. L2 is going to be, again, the function evaluated at those x values. And I do that by plugging it into the equation bar at the very top there. And I go back and double check what the heck was my function in this problem. It was 9 minus x squared. So I'm going to type that in. 9 minus, I don't type in x squared though. I type in where my x values are. And my x values are in L1. So I go ahead and hit second L1. So I'm going to do 9 minus L1. But I want that L1 squared. I go ahead and press enter. And it does all those calculations for me. We already know, though, that at 3, it's going to equal to 0 because you can kind of see it right there, right? But now we can guarantee it. It's 9 minus 3 squared, and that's just going to come out as 0. All the differences on here is going to be by 0.5s, which is already done for me. I'm going to go to L4 and calculate the areas here. Again, I'm just going to go to the very top, let this equal to every number that's in L2, and have that multiply by every number that's in L3. Press enter, bam, those are all the areas of each of these little rectangles right here. So I have 4.375 is this area right here, right? Over here I have 4, and so on and so forth, all those values calculated. And wait, is that right? 4? 9 minus 1 squared. That doesn't seem right. Oh yeah, the width. Yeah, that's right. That is 4. That is right. The height was 8, but in times by 0.5. Yeah, knock me. Come on. Now. All right, so I have all these areas. I'm gonna go ahead and hit second quit to come back to my home screen. And again, I'm gonna tell my calculator to go second stat. I want to go to math, and I want to go ahead and sum up those values. So I press sum. It doesn't know where to sum. I have to tell it sum all the numbers in L4 for me, and that tells me that the sum of those areas is going to be 15.625. 15.625. That's that guy right there. Okay, let's see here. All right, let's keep going. Let's keep going. Okay. Let's take a look here. Whoops. So I wanted to show you just in case like you don't have. Nah, that's fine. We're just gonna keep going here. We're gonna go ahead and do these midpoint ones. I'm gonna ask you guys to do that one on your own. Just check this out though. When you do the midpoint rectangles, right? When you do the midpoint rectangles, check this out. You still have the same widths, right? We're still doing it for all of them. Where's quit? Oh, sorry. If you're in the list and you want to quit out of there, you hit second and then mode. You see the word right there, quit. Let me show it with my mouse here. So quit is in blue, so you need to hit the blue button, which then shows you this little up arrow right there, and then we hit mode, and it quits you back out to the home screen. Yeah, so that's how you get back to the home screen, where Blinky is, where you can type in your calculation stuff. Okay, all right. So what I want you guys to do on your own time is fill out or calculate the one for the midpoint right here. So check this out. I'm going to do this one in purple right here. The widths are still going to be the same from here to here, right? It's still 0.5, 0.5, 0.5, 0.5, and 0.5 all the way here. We got 6 rectangles this way, but this time I want the midpoint values. So I don't want 0, 0.5, 1.5. Oh, geez, knock me. 0.5, 1, 1.5, 2, 2.5, and 3. I want the midpoint values of these ones, right? So what's the midpoint between 0 and 1.5? What's the midpoint between 0 and 1.5? What would it be right here? What would that value be? What's between 0 and 1.5? Oh, you guys already told me. It's 0.25. That's right. So your x values are going to be 0.25. What's this one going to be? What's between 0.5 and 1? What's that one going to be equal to? What's between 0.5 and 1? What's the midpoint between there? Any ideas? Any ideas? 0.75. That's right. And the midpoint between 1 and 1.5 is going to be 1.25, and so on and so forth. So those are the values that you would be using to get your heights, right? So the height of this rectangle would go to this midpoint right here, and that would be your rectangle, wouldn't it? And then this one right here would be this midpoint right here to get that rectangle like so, and so on and so forth. So you'd be using the midpoint values between these 0.5s all the way through. Make your rectangles a little bit better looking than mine. There we go. So that's the idea for your midpoint. So do the calculation, practice that on your own, and see if you can get the same answers. I'll just give you the answer for this one for today. But I do expect you to practice it. Try it out on your calculator. Try it out on there to see what you get. Now, the answer you should get, by the way, is going to be 18.0625 is what I got in the past. So just try that out and see what you get. Okay? If you don't have access to your TI calculator, again, let me know. I can get it for you. In the meantime, if you really wanted to, you could use Google Sheets. Google Sheets works the same way as what we just did. Actually, I don't need to show you this, but I like showing you this. Google Sheets. Let's go over here. Let me open up a blank one for you so I can show you. It works the same way, except, well, you'll see. So L1 would just be like your A section right here. So you would type in the numbers that we have over here. Let's just make this up real quick. It's going to be, let's do the L1. Let's do the L values real quick here. I'm just going to cheat here. So let's say 0, 0.5, 1, 1.5, 2, 2.5. This is when we were doing the L RAM, right? L RAM. Calculating Google Sheets is a hassle, just a little bit. So for B, right? B is going to be, now here's the thing. You need to write it out like this. You write down equals, right? And what it equals to is going to be 9 minus A1 squared. So what that does is it does the operations. I use the caret there, right? So it does 9 minus A1 squared. You press enter, and check it out. It does autofill suggested for you right here. But if you don't have it do that, check this out. So it does the calculation right there, right? It comes out as 9. If you drag the corner here and drag it all the way down, it'll do it for the rest of the numbers. You see that? So you have to do a little bit more work. But also you have to type in, you have to understand like cell coding. So like, see here, it's going, oh, take the number from A, square it, and then subtract it from 9. Then for part C right here, we still put in the widths of each one. So it's going to be 0.5, 0.5. And if you repeat them, you should be able to drag and have it repeat for all of them. And then right here, this is where I want to multiply the two numbers together. So I want to multiply the numbers in B1. Now be careful, if you want formulas, you have to set equals first. B1, and I want that to multiply with C1. You see that? And go ahead and press enter. And okay, all right, fine, Google, autofill it for me. And we'll go ahead and have these numbers right here. And when you highlight all those numbers right there, if you look at the bottom right, it has a sum for you. And the sum was 20.125. So you can use Google Sheets for now if you don't have access to a TI calculator. But I just didn't really want to show it to you because on the AP exam you won't be able to. But for practice sake, this is one way for you to do it. But yeah, there you go. It's kind of neat. Also, if you're doing on Google Sheets, this is for 6 rectangles, right? If you want to go to 100, you could highlight this right here and then just have it drag down to, like, let's say I want to go to 20. Boom. See that? And then I can have it continue. So, hey, can you do that and continue it over here? You see that? And have it go over here and drag that all the way down like so. So you can just drag and you don't have to repeatedly type in numbers. So that's one cool thing about Sheets. Again, Sheets is nice. Desmos is nice as well. It does that for you as well. It just, you can't use these things during the AP exam. But it's cool for your own sake and for your own knowledge. Anyways, that's for that. The midpoint one, like I said, try it out with the 6 values for the midpoint. You should get 18.0625. If you don't get that, then something went wrong. Now, what I wanted to show you was this one right here. Riemann Sums does not necessarily need to have the same width all the way across. You could pick random widths and you'll still get an approximation, right? You can still pick random, you can get random width and still get an approximation here. So suppose delta x of k has a width equal to 0.5. Choose random value for x of k in each interval and compute the area of each Riemann sum rectangle. So what I'm saying is if you just pick a random number, give me a random number between what's a good random number? Someone give me a random number, like a random small number. 3? I'm sorry. Give me a random number that's between 0 and 3, because that's the interval that we're dealing with. 0.3446. I like it. So let's go right here. This point right here. This random point of 0.3446. Right? So if I use that as my x value, right there, but my delta x is still by 0.5, guess what the next one's going to be? The next value would be, so my first x value in my x list right here would be 0.3446 because David is typing out that number for me. Oh, Emily went with 2. We could have went with that too, but you know, it's a little bit easier to see when we put these little decimals here. So if the delta x's are equal to 0.5 each, to get from here to the next number, then this next one would be 0.8446, right? Because all I'm going to do is to go from the next one to this one, I'm going to add by 0.5, because that's what the delta x represents, right? To go from one x value to the next. How much is your x changing? And what I wanted to show you is this. If I go by 0.5 again, this would be 1.3446. This next one would be 2.8446. This next one would be, wait, what? Knock me? 1.8446, 2.3446, and then that's 1, 2, 3, 4, 5 rectangles. We just need one more, 2.8446. These would be my 6 rectangles now. And I just picked like random values instead of doing LRAM or RRAM or MRAM. I just picked random number, and then I just made my rectangles based off of these guys right here. And whoops. And what I wanted to show you guys is you can still do approximation calculations with different numbers that are in there. Now, why do I bring this up? There are cases where you're not going to have the function given to you. Instead, you're going to be given a table. And on that table, you kind of have to get the output values based off of the table. In this particular case, we have the function, so we can just type this into our calculator and have it do it for us. You calculate this out, calculate the area, you'll get an area that's going to be around these values. About, well, LRAM was an over approximation, RRAM was an under approximation, so it should be around 20 and 15 is what I'm saying. So if you pick random x values and do this approximation, these Riemann sums, you'll still get a nice approximation of the area underneath this curve. So, you know, like I said, it'll be this one right here to get this weird rectangle to go from, it's not going to go from there to there, though. It's going to go from like there to 0.8. So 0.8 would be like right here. But, you know, that's just stuff that for you to try out. So I suggest you try this out. You can try with the numbers I plugged in here and see what you guys get for your area for this. What would the area approximately be if you're just using these numbers? So again, I suggest you practice this and get these y values, right? And then multiply it by the delta x. Delta x in all these cases is still 0.5 all the way through. And then give me the area of each of the rectangles, right? Area of each of the rectangles there. And see what you guys get for that one. I want to see this in your notes. So just you don't have to use these numbers. This is the number that David randomly picked. And then I went by 0.5s. I just added 0.5 all the way through there. You see that? And that's how that works. Once you get that done, the next thing I would ask you guys to do is to pick 6 randomly sized intervals between 0 and 3. So this is the next part of this notes that I want you to do on your own. I want you to pick 6 random points in between 0 and 3. Don't pick the ones that we already did. Don't pick like 0.5 and 1.5. Like I legit want random numbers. So like, for example, you could pick, like David already picked one, 0.3446. That's one of them, right? That's one of them. And that's going to be the height there. Emily was kind enough to give me another number. That was 2. We can go with that. And 2 would be right here. So I'd need like 3 more random numbers. And you guys get to decide. Like I would go with like maybe, I don't know, 1.7. No. Let's go with like 0.83. And then this one could be like 1.2. And then this could be like 2.6. So those are like my 5 random points there. And the only thing is, if you pick random numbers like this, your delta x's are going to be different now. The delta x from here to here, right, is different from the delta x from here to here. And you have to calculate that for your L3 or your, see, before it was always 0.5. If you do something like this, to get the new delta x's, you just have to subtract them. So I would subtract 0.83 minus 0.3446, and that will be my new delta x for this distance right here. So that's what I want you guys to do here. Pick 6 random points and then draw, calculate the area, estimate the area underneath the curve with those random points down there. I did this last year. Let me show you what this looks like. We don't have enough time, so I'm just going to show you this one right here from what I did last year. Since we have shortened time here. This is what we did last year. So I had the kids in class pick random numbers and we calculated it together. What the heck? Undo. Hold up. I just realized what I tried to do there. Sorry. All right, there we go. All right. There we go. So this is what we did last year. All right, this is what we did last year. We picked 6 random points there. We calculated the delta x's between all those 6 random points. And then we calculated the area here, and we got about 15.05, which was still about, similar to it. So that's what we did. We did it as an RAM with those values right there. So we did that curve. But anyways, that's the idea. I wanted to show you that you don't have to have your delta x's to be equal to 0.5 every single time. It is possible to still do it, and you still can get it on there. Anyways, there's a second example here. I want you guys to try this one on your own at home for homework, right? See what you guys can do here and get that right there. Answer part A, okay? So get your L, and you're going to be using 8 rectangles. So for your 8 rectangles, let's just practice here. What should your delta x be? Your delta x is not going to be 0.5 for this one up here. Up here, your delta x is going to be equal to 3 minus -1 over however many rectangles. In this case, we want 8 rectangles. So that's going to be equal to 3 minus -1, which is going to be 4 over 8, which comes out to 1/2. Oh, it does come out to 0.5. So your delta x is still going to be 0.5 for these ones. So you guys can do that one later. And then, choose your randomly 8-sized intervals. Give me the total area for that one. But here is where it comes into what I think someone was pointing out earlier. What makes this calculus? And this is what I wanted to get into right here. So do this one on your own. We're going to come over here, though. Follow with me right now for your notes right here. So far, we haven't applied any calculus. We've only done geometry. Calculus always requires the use of a limit. And that's what somebody was pointing out earlier. You guys saw what happens, right, as I start getting more and more rectangles. When I got up to 100 rectangles, my area became very, very accurate. It was still being cut off a little bit here and there, right? But if I take the limit as n goes towards infinity, right? As n goes towards infinity. This one's a little bit different here. This is the idea that the delta x is going to go to 0, right? So as n goes towards infinity, the widths of each of these rectangles get infinitely smaller, right? Till it becomes almost 0. So we got to see, what does it approach as that approaches 0? And what that approaches is just the area underneath the curve to the exact value. You're no longer doing it as an estimate. It gives you the spot on exact value of what it is. And I did not get this ready, but the idea is this, right? Actually, if I could just Google it, maybe it'll come up. Riemann Sums. See here, check this out. Would it be here? Would this one work? As I increase the number of rectangles, as n goes off towards infinity, the delta x's, the widths of each of these rectangles get smaller and smaller, right? And eventually, as it goes off towards infinity, the widths get infinitely small. It approaches 0. And once it approaches 0, you get a nice, perfect representation of the area underneath the curve. This one stops before it gets to infinity, which kind of bothers me. Do you go off towards infinity? Oh, what are you going to say? No, darn you. Darn you all. Oh, there we go. That's a good one. Can you guys see that? Yeah, let's go take a look at this guy. Yeah, so you guys see that right there? As it gets infinitely smaller and smaller, right, it gets more and more accurate. And actually, as it gets to infinity, as the delta x gets to 0, right, as the limit as we get to there, it'll just equal to what that area is. So Riemann sums is a technique that we use to calculate the area underneath that curve. And if you do it with infinitely many sums or infinitely many rectangles, you get the exact value. Now, in calculus, we call that an integral. This guy right here. An integral represents the summation of all those rectangles, but there's infinitely many from A to B. Now, that's all it's doing. It's calculating the limit as x goes towards, the delta x goes to 0, or the number of rectangles, you want to think of it that way, goes off towards infinity. Okay? In this particular case, they're letting this one go to 0. So that's the idea here. So that integral, this guy, this symbol right here, will calculate the area underneath the curve for you. Now, your calculator does this integral calculation for you. It does a Riemann sum with the delta x being equal to a very, very small number. It equals to 0.0001. And it computes the area of each rectangle and gives you the total of all the rectangles from A to B. So your calculator does this integral for you. So check this out. We're going to use our calculator to do this for us right now just to practice this. I'm sorry if you don't have access to your TI calculator. I don't know if fnint is a function on Excel sheets or Google Sheets or Microsoft Excel. It probably is, but I don't know that one. We could Google it. But for right now, I'm going to show you real quick here. Watch this. All right, we're going to go ahead and calculate the area underneath this curve right here. So let's say I have the function x squared, and I want to calculate the area from 0 to 2. Here's how we do it on our TI calculator. You ready? We're going to look for this function called fnint. So on the home screen, you're going to press math and scroll down. fnint is option number 9 under math. Go ahead and press that. When you go there, if you have the newer ones and you press fnint, it's going to look like this, and you actually see the integral symbol. If you have an older calculator, like the TI-83, it won't look like this. It won't look like this. If you have the TI-83, when you type this, it'll actually look like this, fnint, and then a parentheses, and you have to type in your function. If that's the case, I suggest you get the directions on how to use fnint, and if not, stop by my office hours. I can show it to you. It's just going to take a little bit of practice. But you have this right here. You actually can see what to type in. So this is going to go from 0 to 2, and inside you just type in the function. This is x squared, and of course we put at the end there dx for delta x, right? That's what that d stands for, by the way, the difference in your x. We go ahead and press enter. Check this out. Bam, it tells me that it's approximately 2.6 repeating. 2.6 repeating, right? And let's go ahead and sketch what this graph would look like. You ready for this? So x squared, right? X squared looks something like this. It looks something like a parabola, doesn't it? Like that, doesn't it? And it's going to go from 0, 1, and 2. What this integral represents with this point 2.6, this 2.6 right here, this guy right here, this 2.6 represents this area from here to here. And that's all an integral does. It calculates this area. And this right here is doing it to very, very precise numbers. And how is it precise? It's very precise in the fact that the delta x is only 0.0001. And that's it right there. That's what that represents. You guys see it? You guys okay with that? Does that kind of make sense? Let's try this next one. No? Where have I lost you, Max? Where have I lost you? How did I get the 2.6, or what does the 2.6 represent? Or something else that I've lost you on? Yeah, what, Max? How does the 2.6 equal to the area? Yeah, okay. So, Max, remember, right? The area underneath the curve is this idea right here. We multiply the function height, right? The height of these rectangles is equal to what the function value is. Multiply it with the base. And the base is how wide each of these rectangles are. Okay, so earlier when we did these RRAMs and LRAMs right here, right, like this one right here, let's say this RRAM right here, we calculated it to be this guy right here by calculating the area of each of these rectangles. But there's only 6 rectangles in total here, right? And these 6 rectangles have a delta x equaling to 0.5, right? And how do I know that that's 0.5? We did this calculation right here, right, of b minus a over n, right? Where n was the number of rectangles. And if I had 6 rectangles, if I was doing it from, in this particular case, from 0 to 3, right? That's how we got that delta x. Now, I'm going on to this other part right here. Delta x they're telling us that we're going to be using is very, very narrow, which is another way of saying the number of rectangles I want it to be infinitely many, right? I want it to be infinitely many. So if you look, let's go ahead and go into Desmos here. What I'm essentially doing, I did not want to save that. So for x squared right here, and I'm going from 0 to 2, like so, going from 0 to 2 right here, right? When we started off with only 6 rectangles, right? And what we're essentially doing is making it more and more. And when you make it more and more here, I don't know if you can see here, but the delta x's get smaller and smaller. You see that? Your delta x's get smaller and smaller. Right? As I keep going, these delta x's just keep getting smaller and smaller all the way up to when I get to 100 here. Right? Can I go past 100? What if I go 1,000? So I can go up to like 200. Right? You see that? And if you look closely, right, it's getting more and more accurate, right? I go 300. I go 400. This is cool. I can just keep going. So when I go up to like 600, see that? It's so almost perfectly accurate, right? You can barely see it when you're looking at it out here. What an integral does, this symbol right here, this integrand right here, you see that, Max? What that integral does is it makes your delta x, right, or at least in theory, your delta x is approaching 0. Meaning your n is approaching infinity. You're having infinitely many rectangles in between there. They're just really squeezed together, right? So as I kept increasing those numbers there. So when I made like n equal to 600, right? If you look, I have to zoom in so much here to get this delta x from here to here. That's a delta x that's from 1.15 to 1.15, 1, 2, 3, 4. So it's 0.004. So this is how number steps and staircases are calculated with integrals? No. No. But that focus back over here. Check this out. Okay. So that's all an integral is, Max. Does that make a little bit more sense of how an integral calculates that area? Right? That's what that symbol means. Okay. And what I'm doing is I'm just plugging this into my calculator. My calculator does an estimate where it gets as small as possible. It can't actually get it to 0. It can only get it to there. Anyways, I'm out of time, guys. It is 10:37. Here's what I want you guys to do for me. I want you guys, for homework, right, finish off your L8, R8, and M8 for example 2. And using your calculator or finding a calculator online, calculate number 4 and calculate number 5 for me. And when we're going to, next time when we come back, we're going to continue where we left off here and try to finish this off next time. All right, guys, other than that, it is 10:37. I can't keep going, but even though I want to, but I need to let you go to your next class. So I'm going to say have a good weekend. I'll see you guys on Monday. Stay out of trouble, stay out of jail, don't get pregnant. All right, I'll see you guys later. Have a good weekend, guys. Goodbye, guys. So long. Farewell.